Good afternoon, students.
Good afternoon, ma'am.
In the last
Good
class, we had
afternoon, ma'am.
seen what is a combinational circuit and what is a sequential circuit. So, we are going to continue that discussion today. I'm going to be presenting my screen now. Please let me know once you can see it.
It is visible, ma'am.
Are you able to see the screen?
Yes, ma'am.
Yes, ma'am.
Are you able to see the screen, students?
Yes, ma'am.
Yes, ma'am.
I'm not able to hear you.
Yes, ma'am, it is visible.
Okay, right. Okay, so let us revise. What is a combinational circuit? So on your screen, you can see that there is a block diagram of a combinational circuit showing n inputs and m outputs. And what is inside this black box? It is a set of interconnected logic gates such as AND, OR, NOT, XOR, XNOR, NAND, NOR, etc. Right? We've already seen these logic gates in detail earlier. I want somebody to read from the screen.
Yes, ma'am.
Who is this?
Dipali.
Sorry, come again.
Dipali.
Right, Dipali. Thank you. Yeah.
You're welcome, ma'am. The digital electronic circuits can be classified as combinational circuits and sequential circuits. A
Sequential
combinational circuit
circuits. Combinational circuits and sequential circuits.
A combinational circuit is an interconnection of logic gates, the elementary building blocks of digital circuits. The outputs of a combinational circuit at any time are a function of only the present inputs to the logic gates.
Okay, this is what I had explained last time. Any problem till here?
No, ma'am.
Right. Yeah, continue.
A sequential
A
circuit,
sequential
li-
circuit.
a sequential circuit,
A sequential circuit.
sequential,
Sequential.
sequential,
But it is a sequential.
sequential.
Sequential circuit, yes.
A sequential circuit, like combinational circuit, is also an interconnection of logic gates, but it also employs a set of memory elements. In contrast to the combinational circuits, the outputs of a sequential circuit are dependent on not only the present inputs but may also be affected by the past inputs. The memory elements, such as flip flops, are responsible for storing the past state of the circuits. As shown in figure 1.1.2, the memory elements form a feedback path to the circuit and thereby control its next state.
Yeah. So you can see here that a sequential circuit is a set of interconnected circuits. That means a combinational circuit itself and memory elements, that is, for example, flip-flops, which are attached, as I explained last time, right? These memory elements are put in to store the output that we get from the combinational circuits. So the outputs are also given out to the user and they're also stored in these memory elements. Now at the next time instant, what are the inputs to this combinational circuit? The external inputs that the user is giving and also the previous output that was stored in the memory elements. So obviously the outputs in a sequential circuit at any given instant of time are not just a function of the given inputs, they also depend upon the previous state, that is the previous output of the sequential circuit. Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, good. So these are the differences between the combinational circuit and a sequential circuit. Can you just read them through, Dipali? We've already gone through them. Just
Yes, ma'am.
read through them so that uh, the topic is completely revised. Okay, yeah.
Combinational circuit. It contains no memory elements. Point number two, the present value of its outputs are determined solely by the present values of its inputs. Point number three, its behavior is described by the set of output functions.
Is this clear,
Sequential,
students?
yes,
Nothing new
ma'am.
here, right? Yeah.
Sequential circuits, it contains memory elements. Point number two, the present value of its outputs are determined by the present value of its inputs and its past state. Point number three, its behavior is described by the set of next state memory functions.
Yeah.
And the set of output functions.
Yeah. So nothing new here. The same things that we have been saying up till now. Is this clear? Any problem anywhere?
No, ma'am.
Okay, right. So now let's proceed to the next topic, that is how to design a combinational circuit. So suppose you are given a question of designing a combinational circuit, how will we proceed? So first we will see the steps that we will follow to design a combinational circuit. And then we will follow through these steps. For the two examples that I quoted in the last class for the combinational circuits, I had quoted two examples for the combinational circuits, namely a half adder and a full adder. So we will see how to design a half adder and a full adder using these steps one by one, okay, from scratch. Is this clear?
Yes, ma'am.
Right.
Yes, ma'am.
Yeah. Dipali, can I request you to again read the
Yes,
steps?
ma'am.
Yeah. Okay.
Given a requirement for the combinational circuit, the process of designing a combinational circuit involves deducing the circuit diagram or Boolean expressions required to implement it. Following steps are generally involved in this process. Drawing a block diagram. The first step for designing a combinational circuit involves clear specification of the objective of the circuit so that its function and requirement is clearly understood. This understanding facilitates the deduction of the number and type of inputs and outputs of the circuit. Each input and output is then associated with a unique symbol. A block diagram summarizes this step of the design process and serves as a fundamental block to promote understandability of a combinational circuit in a glance.
So is this
Derivation.
clear, students? What does a block diagram do? What is the job of a block diagram? See, what is a block diagram? First of all, we make block diagrams for many types types of circuits, not just the combinational circuits. But what is a block diagram? A block diagram is basically, as the name suggests, it is used only to specify the function that a particular circuit is required to perform. Okay, so the only thing that we indicate in such a diagram is the inputs that are coming to this diagram, the outputs that come out of this diagram, and for the actual circuit or the process that we want to represent, we just represent it by a box. Okay, a simple box with a name of the process or the circuit. Okay, that is the block diagram. So somebody might ask us, what is the use of drawing a block diagram? After all, we are just drawing a rectangular shape there, right, in between, and just pointing out the inputs and the outputs. What is the purpose that such a diagram can serve? The basic idea is that such kind of a diagram serves as a starting point. Okay, so when we don't want to, first of all, involve ourselves in a detailed design, okay, and rather just see a overall design of the system, of the complete system. That system may be a process, it may be a circuit. Okay, so the idea behind drawing a block diagram is that we don't want to go into the complexities at this time instant. What we just want to see is that we are just going to restrict ourselves to looking at how many input variables will come to this particular box, black box that I've drawn in between, and how many outputs will uh, emanate from this box, and what is the purpose that this box is to achieve. Okay, so the idea is just to put down a objective and clarify the number of inputs and outputs and the function that is required to be done. How the function will be done, that is what is the actual design. We will come to it later. Is this clear?
Yes, ma'am.
Yes, ma'am.
Right. So you can see that its function, it, it involves clear specification of the objective of the circuit so that its function and requirement is clearly understood. This is the main function of a block diagram. Okay? Yeah.
Yes, ma'am.
Next step, derivation of truth tables. Yes, Dipari, can you please read?
The second step of the design process concerns actually studying how the outputs can be obtained from the inputs. For this, generally a tabular representation is drawn up that lists all valid combinations of the input values to the circuit under design and their corresponding output values. The input values correspond to the 2 to the power n binary numbers derivable from the n input variables.
Variables.
This tabular representation is referred as a truth table.
So the second step is to draw the truth table. So in the next step, what are we doing? We are listing the input variables on the one side and the output variable on the other side. And then we list down all the input variable combinations, Boolean combinations for the input variables, and the value that the function should produce for each particular input combination. Okay. So the next step is to draw a truth table according to the function of the particular circuit. Is this clear?
Yes, ma'am.
Yes, ma'am.
Right. Yeah. Let's go over to the next step.
Derivation of Boolean expressions. The next step of the design process involves extracting a Boolean expression for each of the output variables from the truth table. This is generally done with the help of techniques such as Boolean algebra, Karnaugh maps, or Cuny-McCluskey's method.
Queen McCluskey's method. Okay. Now, so the next step is that once we've drawn the truth table, we derive the Boolean expression corresponding to the function, to the output function f. Okay, as we have seen in the Karnaugh maps. So what do we do in Karnaugh maps? We used to have a truth table. From that truth table, we drew the corresponding Karnaugh map and we got the reduced expression using Karnaugh maps. The same thing could be done using Boolean algebra or Queen McCluskey's method, but this is not in your course. Okay, the other two methods we have seen. Next step.
Circuit diagram and its verification.
So
The
then
design process.
after we have the Boolean expression in its most reduced form, the next step would be to draw its circuit diagram. Okay, this would be the final step. So we started with nothing. We started with just the definition of the function, that is what this circuit should do. We drew a block diagram, then we went on to make a truth table, then derive the Boolean expression, and now we are going to draw the actual circuit diagram. Okay, yeah, you can just read it through, Dipali.
The design process of a combinational circuit culminates in a circuit diagram. Each Boolean expression obtained in the previous step is laid down with the help of electronic gates. It is also important to verify the obtained circuit diagram. This may be done manually by hand or through a
Simulation
simultation
program.
program.
Yeah. So the idea is to draw the circuit diagram and then verify it by hand that we've drawn it correctly, and it is giving us the output that it was uh, made to achieve. And this may be done manually, or this verification may be done through a computer program that works up the circuit and gets the desired result. This kind of a program is known as a simulation program. Okay, so these are the 4 steps that are generally involved when we design any combinational circuit. Thank you, Dipali.
You're welcome, ma'am.
Now we are going to see the design of half adder and full adder as examples of the combinational circuits. Okay, so let us see what is an adder. Will somebody else read now?
Yeah, ma'am.
Who is this?
I'm Garima.
Couldn't catch your name.
I'm Garima.
Garima, yeah. Thank you, Garima.
You're welcome, ma'am. Adders. Binary addition is a commonly required computation in computer systems. The combinational circuit used to add two or more binary number is called an adder. A half adder is used to perform addition of 2 bits while a full adder is used to perform addition of 3 bits. The subsections 1.4.1 and 1.4.2 discuss the design of a half adder and a full adder respectively.
Yeah. So is this clear? I had given the definition. I had discussed what is a half adder and what is a full adder with you. So a half adder is used to add only 2 bits of information, whereas a full adder is used to add 3 bits of information. Let us look more at it now. We are going to be doing this in more detail. Yeah, very much.
half adder, given the two bits to be added as inputs, namely the organ and the addend,
So
the
what are
object
these two bits known as? What are the two bits? What are any two numbers which are to be added known as? Mathematically, they are known as the
Organ then
organ
added.
and the addend.
addend.
Okay. So we what we want to do is actually x plus y. Okay, where x and y in this case are Boolean variables. So we are going to be adding two bits here, right? So let x be the organ and y be the addend. Yeah.
The objective of a half adder is to generate their sum and carry. The
So
term
obviously, the objective of any adder is actually to generate their sum and a carry if there is any, right? Yeah.
the term organd is derived from Latin word organdum, which means to be increased. It denotes a number in the addition operation to which another number is to be added. The term addend denotes a number that is to be added to the organd. Figure 1.4.1.1 sum up this information in the form of a block diagram.
So here you can see this is the first step as we had discussed. The first step we will do what? We will draw the block diagram. So we I have just drawn the block diagram here. So what have we done? We have looked at what this particular circuit, which we will call as the half adder, is required to achieve. It is required to take in two inputs, namely x and y or organ and addend, and produce the two outputs, namely sum and carry. And then what I've done is for the adder itself, I've just placed a block here. I've just placed a rectangular block here and named it as half adder. Is this clear? Is this
Yes,
clear,
ma'am.
students?
Yes.
Yes, ma'am.
Right. So we have done the first step by drawing the half adder. Yeah.
The addition of two binary digits bits is carried out as illustrated in the figure 1.4.2.1. The carry in the first three cases is 0. However, in the fourth case, when both organd and addend are 1, the result of their addition is 1 0, wherein the 0 is retained as the sum and 1 is the carry out.
Yeah. Let me just explain this. So let us look at the various cases. So the first case is that both x and y, that is the organ and addend, are 0 and 0. X has the value 0 and y also has the value 0. Right, students?
Yes,
Yes,
ma'am.
ma'am.
So what will be their sum? 0 plus 0 would be,
0.
Zero.
and what would be the carry?
Zero.
0.
0 again. Right? Yeah. Let us look at the next case now. So x is 0 and y is 1. That is the organ is 0 and the addend is 1. So 0 plus 1 will give me a 1
1.
in the sum.
One.
1 as the sum. And is there any carry?
No,
No.
ma'am.
Right.
No, ma'am. No, ma'am.
Now let us look at the third case. This is just the same as the second case, except that the organ and the addend are reversed. That means organ has become addend has become organ in this case. So the organ is 1 and addend is 0. So as in the previous case, I get 1 as the sum, and there is again obviously no carry, right? So the carry is 0. Let us look at the fourth case now. Now, please see, I have both the organ and the addend as ones. So 1 plus 1 is what? 1 plus 1 gives me a,
One
One.
zero.
it gives me a 2. Yes, it should give me a 2, right? 1 plus 1 gives me a 2 in decimal number system, right? So this is okay, but how do I write it in binary?
1 0.
1-0.
Binary, it is
One.
written as 1 0. So as usual, this first bit, right, this first bit is retained as the sum bit, and this second bit, this is taken as the carry. Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So 0 is retained as the sum bit and 1 is taken as the carry. Any problem?
No, ma'am. No, ma'am.
Right. So now that we are clear about the output that should be produced for each set of inputs, what are we going to do? We are just going to list all this in a tabular fashion in the truth table. Okay. Yeah. Garima, can you read?
Yes, ma'am. The truth table of a half adder can be drawn corresponding to the combination of the two input variables augend and addend, say x and y respectively, and their corresponding outputs sum and carry, say s and c respectively, as illustrated in figure 1.4.2.1.
Okay, so what you can see here is, you can see here the truth table. So this is the organ, this is the addend. And so 0, 0, the sum was 0 and the carry was also,
Zero.
Zero.
yeah. In the next case, organ is 0, addend is 1, the sum is,
1,
One.
One.
and the carry is,
0.
Zero.
Zero.
same is the case for the third row, yes or no?
Yes.
Yes,
Yes.
ma'am.
Yes.
Let us
Yes,
look at
ma'am.
the fourth case now. So both organ and addend are 1. So what is the sum that is produced? It is,
Zero.
Zero. Zero.
and
Mm,
there is a
0.
carry of 1.
One.
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 Any problem?
1.
No, ma'am.
No,
No,
This
ma'am.
is
ma'am.
how binary
No, ma'am.
addition of 2 bits is done. Okay. Now what is the next step? We've drawn the block diagram. Next we've drawn the truth table. The next step is to
Circuit diagram.
derive the Boolean expressions. Okay. Now usually please see we had generally had a single, the truth tables that you've seen so far had a single output variable, right? But this time, as it was shown in the block diagram, we have how many output variables now?
Two.
2.
Two.
Namely, sum and the
Carry.
Carry.
carry. So for each of these, obviously we require a Boolean expression. Okay. So first we will obtain the Boolean expression for the sum, and then we will obtain the Boolean expression for carry. Now please see, uh, we could have done directly, what we could have done directly is that we could have directly drawn a Carnot map for sum and a Carnot map for carry, okay, and got their expressions, as we have learned how to solve the Carnot maps with our knowledge that we have gained, right? But in this case, if you see, let's see this carry. So here you can see that I am simply getting a single one here. Yes or no?
Yes,
Yes,
ma'am.
ma'am.
Yes,
It is
ma'am.
going to be a two variable Carnot. Okay, let me draw it for you. So for carry output of the half adder, I'm going to be drawing this Carnot map. Okay.
Ma'am,
So
are you sharing the screen?
are you not able to see it?
No, ma'am.
No,
It's not
ma'am.
visible.
No,
Okay.
ma'am.
Okay, just give me a second. I'll share. Yeah, can you see it now?
Yes, ma'am.
So what I'm doing is I'm drawing the Carnot map for the carry output. If you wish, you can also draw it side by side on a piece of paper. Okay, so what do I get? I'll put a one here. That is it. Yes or no? Yes or no, students?
Yes, ma'am.
That is it. We only got a one for the last uh, input combination in the carry,
Yes, ma'am.
right? So what will I have as the output? Is any grouping possible?
No, ma'am.
No, ma'am.
No, ma'am.
So what will I get? What is the Boolean expression that I'll get? Carry is equal to xy.
XY.
Any problem?
No,
No,
ma'am.
ma'am.
Right? Okay. Now let us draw Boolean expression. Let us derive the Boolean expression for the sum.
Ma'am, it should be y dash and y.
Yeah, whatever written. Okay,
Ma'am.
sorry. Yeah, forgot to edit. Right. So sum was 1 when we had 0, 1, x as 0 and y as 1. Yes.
Yes, ma'am.
Yes, ma'am.
And when x was 1 and y was 0. Right. So this is the Carnot map for the sum function. Is this clear?
Yes, ma'am.
Yes, ma'am.
Is there any grouping possible?
No,
No,
ma'am.
ma'am. No,
No,
ma'am.
ma'am.
No.
No, ma'am.
Yes. So what will I do? I will simply write down the min terms corresponding to these two terms. What is this? This is x dash y, right?
Yes,
Yes,
ma'am.
ma'am.
Okay. And what is this? This is
XY dash.
x
XY
y
dash.
dash. Any problem?
No, ma'am.
If you remember, what is this logic operation?
XOR.
Yes, A
Or.
dash B or AB dash was equal to A
X.
XOR B.
Yes, ma'am.
Do you remember?
Yes,
Yes, ma'am.
ma'am.
So actually sum is equal to X XOR
Why?
Y. Right. So please see. So what do I get? So this is the circuit diagram. Let us draw the circuit diagram of this half adder now. So what is the circuit diagram of the half adder? So let's say if my inputs were A and B, then I ANDed them. When I ANDed them, I got the carry AB, and the same inputs I XORed and got my sum. Okay, so this is what you see on your screen as the circuit diagram for the half adder now. Is this clear, students?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Any problem to anybody?
No, ma'am.
If you want me to explain anything, I will explain again. Please see. So here again you can see. So sum was equal to x dash y or xy dash, that is xx or y, and carry is equal to xy, right? So this is the circuit diagram for the half adder. So my process for designing the half adder is complete. Is this clear?
Yes, ma'am.
Yes,
Yes,
ma'am.
If
ma'am.
you are
Yes,
told to
ma'am.
design any combinational circuit, you are going to perform all these, you're going to show all these steps. Is this clear? Right?
Yes.
Yes, ma'am.
Yes,
Okay.
ma'am.
Yeah. So students, I have shared the attendance with you, link for the attendance. Please mark your attendance for theory. Okay. Next time we are going to look at the full adder. Okay. Full
Ma'am, I
adder,
see
and
my roll
then we will
number.
also look at the half subtractor and full subtractor. Most probably in the next class we should be able to complete all these three. Okay. Then after that, the next class we will look at the sequential circuits. Right?
Yes, ma'am.